Good morning, everyone. I'm Fang Chuanjie from Zhejiang University. It's very happy to share my work with all of you. My work. Okay. My work. Okay. Okay, my work is focused on the surface effect tear the polymer membranes with integrated extra thin separation layer for the nanofiltration membrane. I'm from Zhejiang University in China, Hangzhou. I will introduce this work from 5 parts. The first part, as we know, we are facing a very serious global water shortage. And also the water now was highly polluted by the several industrial fabrication and also lots of the purifiers. Until now, in the more than 80 countries or areas face this such shortage. And also the water quality is very more serious than the water quantity based on the Professor Angela. So now we should solve the water crisis. As we know, membrane technology is a very good method to solve this issue because we only use the physical filtration can make the solutes in the water can be removed by membrane, so we can get a very clean drinking water over the water for industry. Among the many membrane technologies, nanofiltration is very good nice because he can remove the solutes in a range from size ranging from the 0.5 to 2 nanometers. So, and use this kind of membrane technology, we can get a very good water. This is available for the people drinking. And as we know, the membrane is the key of this technology. Until prepare the membrane with high performance, including the high selectivity and high resistance. And until now, there are two kind of membranes. One is RSA, another one is TFC. RS membrane has a good structure stability and easy fabrication, but the separation layer was thick. Usually, this kind of membrane for nanotechnology has a low water permeance, but the TFC has a high water permeance because the separation layer was very thin. But this kind of membrane has a very big shortage. This is the individual instability. Usually, this kind of membrane uses the serious environments, including the acid or airline or organic solvent, something. And in these cases, this kind of membrane cannot get a very good performance. So having possibly the equations, if we want to get a membrane with a good performance, we should make this membrane has high porosity and for the pore size and lower the thickness and decrease the membrane pores porosity. So we can summarize some ideal structures: the ultra low thickness or the high porosity, and the narrow the pore size distribution and the stable structure. But even though we know the principle to make the membrane has a good performance, but how to do this is a big challenge for the membrane scientists or the engineers. So usually for the membrane fabrication, two methods will be focused. One is the phase phase separation. Another one is the interfacial polymerization. In this work, we developed a new method based on the polymer surface effect. As we know, the polymer has the glass transition glass temperatures. That means on the membrane the surface, the membrane the Tg was lower than the membrane the Voic. That means the polymer chains on the surface was more active than the membrane the Voic. If we use this principle, we can prepare a membrane with a very thin separation layers based using the IS membrane tabs, not for the TFC. Because we want to prepare the TFC membrane. If we want to prepare a very thin separation layer, we use the other method. But this kind of membrane interfacial instability. This is good for some special applications. So based on this scenario, so I prepared a very good nanofil membrane. It's very easy to understand. The initial time, I will use the phase separation method to prepare ultrafusion, UF membranes. This kind of membrane has many pores on the surface, as shown here. And after that, I use the summer treatments, and this the membrane was the temperature was controlled below the membrane the polymer Tg. After several the summer treatments, the membrane surface, the porous surface will become very thin, dense surface. This kind of dense surface will be the separation layer of this membrane, but this separation layer was combined with the Voic without any interface, and also the thickness will be controlled less than 100 nanometers, similar to the surface of the TFC membranes. Okay, here, and this kind of membranes can give the membrane very high performance. At initial time, we should know in this work, I use the PES as a polymer to make the membrane. Initial time, I should check the PES Tg. I use the DSC. We can see the PES Tg was at 231.2 degree, and also another method, and the MA also checked the PES Tg similar, has no big difference. This kind of membrane Tg was along the 230 degrees. After that, we based on this kind of temperature, we should determine which temperature we should use to give the membrane a very thin, dense layer. So based on the prepared membrane, we use the sign and check the membrane, the surface and the Voic lining the patterns, and also we use the software to check the pore size and the porosity of these parts. Based on the different porosity, we check the surface. The Tg was 214 degrees. Also at this part, the Tg was 226 degrees, and also the Voic part was 237 degrees. And also, so based on this kind of different temperatures, and if we control the treated membranes at around the 240 degrees, we can get a membrane with a very good thin and dense surface to give the membrane good separation layers. So based on these characters, we decide several the temperatures and several times to summer treat the membranes. Initial time we can see this is the ultrafiltration membrane, UF membranes. We can see lots of pores on the surface, and at the temperature of the 226, also the membrane has a lot of the pores, tiny pores, and compared to the UF membranes, this kind of more the size decreased sharply. And after 4 hours, 4 hours and 4 hours treatments, the pores was clearly disappeared, and 2 to 8 hours we can see the membrane was completely dense. That means this method was can successfully give membrane a thin and dense separation layers. Okay, and also here we can see the clearly the shade. And after that, we also check the membrane, the cross section, the structures morphology. We can see after 6 hours treatments, the membrane has a very thin dense separation layers. The thickness was around 88. And also we can see from here, if the temperature was lower than for example, 232 degrees, we cannot see the very thin separation layers. And another case, if the temperature was very high, close to the STG, for example, the 236 degree, we can see the bulk was changed without any pores. That means the not only surface and the bulk was changed to the very, very dense structures. That means in this case, the membrane, the permeance will be very low. And also, so we can see only with the shipboard temperature and times, we can give the membrane only the very dense separation layers without any change on the membrane bulk. The membrane bulk also has a very porous structure. The surface have very thin separation. This kind of membrane similar to the TFC tips, different from the conventional AS membranes. And also we use the FTIR and the potential to check the membrane, the chemical structure. Also, we can see after the summer treatments, the membrane structures, the chemical structure without any change. That means here there's no any chemical reactions. Only the polymer, the chains, active motion happens. And also we can see from here. Okay, I will show a little quick. And also after this pH, and this is also electrical point, is without any change, is 4.622. And here we can see the performance after with increased temperature, the water permeance decreased and the rejection increased to from the 0 to 19.2. This can solutes is 1,302 Da. And also with increased time, the permins decrease, the VB2, the rejection increased. That means this can operate clearly from the UF to NF. And also this membrane, the pressure resistance, we can see from here, the membrane has a good the pressure resistance. And also after the 30 hours checking, the membrane performance was very stable. And this is the membrane the rejection. And we can see we use some line to check the membrane the molecule cut off. Membrane the molecule cut off is along the 600. This is the typical the nanofiltration membranes. The solutes, the salt rejection we can see here. The for example, the sodium sulfate rejection up to the 98% or 90%. That means that this also can confirm this can operate was a nanofiltration membrane. This is the membrane, the mechanical properties we can see with increased temperature and the time, the membrane, the mechanical strength increased. That because the membrane surface was changed from the porous to dense. So the mechanical property increased. This kind of membrane, the resistant to acid, we can see after the being immersed in the 8% in the hydrogen sulfurant and for 4 hours, membrane surface, the membrane performance did not change very well. That means the membrane has a good the acid resistance and also compared to the commercial TF membrane and the commercial AS membrane. Our membrane have very good performance and also have a good resistance for some special applications. Okay, I can conclude my work here. I use the special method to prepare a new PES membrane, NF membranes, and also this kind of membrane, the what permins up to the AMH bar, and also the molecule cut off is 600 Da, and also this kind of membrane was only prepared by the physical method, not the chemical method, without any the cross-linking or the chemical grafting or something. And here I also change the PhD the students and the Chuanjie, and also thanks the many the support for support this work, and also thanks very much for the Professor Hiba gave me the chance to share my work for all of you, and also working Egypt's professor to come to China and Zhejiang University for some academic communication and share our works. Have a very good chance. Thank you very much.